Nicholas Flamel. Nicholas Flamel. Nicholas Flamel.
Hey, who's there? I heard somebody. Harry Potter. This is the restricted section of the library. What are you doing here?
Well, how'd you see me?
Well, if a bedsheet's supposed to work as an invisibility cloak, you're not doing a very good job.
Oh, I saw in a movie one time. How do you create an invisibility cloak?
It's funny you ask. You see, invisibility might have been something only before seen in books and movies, but science has gotten us a lot closer than you might think. Take this leaf and this particle of light. When light hits this leaf, it can either be reflected, scattered, or absorbed. But what if instead light was bent around this object so that we never actually get to see it there? Well, in 2006, that's exactly what researchers at Duke University did. Using a periodic array of copper split ring structures in an insulating matrix, they were able to bend certain electromagnetic radiation around the arrangement, rendering it invisible to microwaves. The copper inclusions are placed millimeters apart, much smaller than the centimeter-long wavelengths of microwave radiation, so that the material can manipulate the incoming light waves in a never-before-seen way. Here we see microwaves being traced through a constant medium without any distortion. When an object is placed in the way, there is a clear disturbance in the microwaves. However, once the cloak is placed around the object, instead of scattering incoming microwaves, the microwaves propagate through the arrangement and form back together on the other side, as if there was nothing there. While this illusion has been theorized for some time, this was the first time successful cloaking had ever been demonstrated. Once engineers have successfully mastered control of how light propagates through a material, we will be able to build things like cloaking devices, super high resolution lenses, and enhanced antennas, to name a few things. However, the higher energy light waves we want to manipulate, the smaller length scales we must use in our designs. One of the most challenging steps to overcome for true invisibility is fabricating these structures at such length scales so that the material is invisible to all wavelengths of visible light at once. Red and blue light waves are a lot smaller than microwaves, for example, and thus the material much harder to fabricate. But that's where I come in. At the Thornton Lab Group, we develop mathematical models for physical systems and run simulations with them to try and match experimental results. Once a model has been rigorously tested, it can be extended to make predictions about other systems and used to develop new materials or processing techniques. I simulate the solidification of eutectic systems. So, what is a eutectic system, and what does it have to do with invisibility? When a binary mixture cools and solidifies, it will often separate into two distinct phases. Usually, one phase will begin to solidify before the other phase. However, at a specific concentration of components in the mixture, or the eutectic concentration, both phases will begin to solidify at the same temperature, producing a periodic microstructure consisting of rods or sheets of each phase. In this example of my simulation results, the red and green represent the two different phases of the solidified material, while the blue represents the liquid. The thickness of the sheets or rods can be controlled by the speed at which the mixture is pulled along a temperature gradient. As the speed of the solidification front is increased, the red and green lamellae split into thinner phases to compensate. This is a diffusion process that is captured in the mathematics used in our computer model. In another simulation, a template represented by the yellow ellipsis is used to disrupt the solidification front. With these simulation results, a template can be used to tailor the structure to specific shapes and designs. Because of the periodicity of the eutectic microstructures, and the fact that they can consist of two very different phases with very different interactions with light, eutectic solidification presents a promising method for self-assembly of metamaterials. The model is based on domain parameters that vary smoothly from 0 to 1 along the interfaces of each phase and change value depending on what phases are present. This model, called a phase field model, simplifies the problem and makes the simulation less computationally expensive. My hope is that my model can be used to predict the structure for larger 3D systems, and eventually used to expedite the discovery of new metamaterials. But it doesn't end there. Eutectic solidification is finding applications in fuel cells, photonic crystals, ionic conductor composites, and even nanowires. And there's still a lot more research to do.